Hello viewers, let's see DG sizing calculation. Before starting DG sizing calculation, we require some data so that base load and peak load we required and large size motor starting and running load we required. Then DG data we required. Based on these three data, we find our DG size with this three method. Let's see step 1, base load calculation or peak load calculations. Here you can see in the tabular column motor A, its rated power is 37 kilowatt and absorbed power is 30.80. The motor is running with 415 volt and we need to know motor A has to be working or standby motor. If it is working, then further we need to know whether it is a continuous running load or intermediate load. If let's see here, next we want to find demand factor of the motor. You can see here C equal to A divided by B. Here A is our absorbed power, B is our rated power. You can find with these two data our demand factor. Same as it is, you can get from motor nameplate this power factor. The efficiency you can get from our Indian standard 12615. You see here, this is our Indian standard tabular column. Our motor is a I3 type. Our motor A load 37 kilowatt and its efficiency is 93.9. So the manufacturer gave us the efficiency is 94.2. Based on this, based on these datas, we want to find our load in kilowatt and kVA and kVAr. You just see below the tabular column. Now we know that total continuous load is 422.64 kilowatt and total kVAr is our 262.48. For intermediate load total kilowatt 67.11, then kVAr 45.07. And also we require to know the continuous load we required 100% or less than 100%. If it is we require 100%, we have to take 1. Then intermediate load we need to take 40 percentage. That is based on your requirement. If it is 40 percentage, then you can choose zero point 0.4. The total duty factor you can find from our total kilowatt. You see here our duty factor is 1. So total kilowatt multiply by 1, we can get total duty factor. As it is same, our intermediate duty factor is 0.4 percentage, not the 0.4, 40 percentage, sorry, 40 percentage. So we can find from our total intermediate load multiply with 40 percentage, we can get 26.84 kilowatt. As it is same, you can get kVAR also. Standby load, no need to take for DG sizing calculation. It act when the main motor is off. So almost only one motor is running during the working condition. Finally, now we know that continuous load, our continuous load is 422.64 kilowatt, and intermediate load kilowatt is 26.84. Finally, we can get our base load demand kVA. This is the formula equal to square root of kilowatt square plus kVAR square. Already we know that kilowatt and kVA. So now this is our kilowatt, total kilowatt, continuous and intermediate load kilowatt. This is the continuous and intermediate load kilowatt, and this is the continuous and intermediate load kVAR. We put in these two data in our formula, we can get base load kVA. You see here in the tablet column, we highlighted on green color. This is our large size motor. So this large size motor kilowatt is 75 kilowatt. You just remember. Finally, we found our base load is 449.48 kilowatt. Our base load kVAR is 280.51 kVAR, and base load kVA is 570.33 kVA. Sorry. DG sizing calculation, we required base load, then we required large size motor starting and running load. So already we know that base load of our DG. Now let's see here, our large size motor kilowatt is 75. You can get from this tabular column, 75 is our large size motor kilowatt, and load factor 0.73 you can get from here also, 0.73. Rated efficiency, rated power factor. These four data we can get from our tabular column. Then starting power factor. So whatever motor during the starting, it will take less power factor based upon the our starter. This power factor we have to assume here for DOL starter zero point 0.2. Our starting coefficient is 1 because we are using for DOL starter. Sometimes this coefficient not required, and we need to know that our large size motor starting through DOL starter or star delta starter or soft starter or VFD. If suppose our large size motor is running with DOL starter, then we have to take 6 times of rated current. Here we take 6 times of rated current. Let's see large motor running load. During the large size motor running, how much load it is taking, that we need to calculate. You can find these three value you can find from our tabular column. This is our kilowatt 57.68. See here 57.68, as it is our kVA 67.51, 67.86 and 35.56, 35.75. Almost it is a equal, or else you can get, or else you can calculate with these formulas. For starting motor, not a starting motor, it is a running motor, kVA. This is a load factor, and multiply with rated kilowatt divided by efficiency of motor into power factor of the motor. You can get the value 67.51 kilowatt. And we need to know that large size motor starting load. So as it is same, the formula is large size motor starting kVA formula is rated kilowatt divided by efficiency in power factor, and multiply with starting current. So starting current, we know that 6 times for the large size motor is starting by DOL. So this you can see here, the 6 is our starting current multiplier. That means our DOL starters, we are using here DOL starter for start the large size motor. That's why we are taking 6 times of rated current. So finally we can get 550 54.93 kVA is our large size motor starting kVA. And second, we have to find large size motor starting kilowatt. From this formula you can get large size motor starting kilowatt. Our starting kilowatt is 110.98, and we can find out our large size motor kVR. The formula is kVA int square root of 1 minus PF square. PF starting means our starting power factor. We can get 543.72 kVR. Finally, the large size motor starting RMS load we need to find. So this is the formula, root square of kilowatt square plus kVR square. So 554.93 kVA is our RMS value of motor load kVA. See the equation number 4 and 7 almost. This is our kVA RMS kVA we find from our derived kilowatt and kVA R, and large size motor kVA also we are calculated here. This equation 4 and 7 almost equal. That means our calculation for large size motor starting calculation is correct. Then let's see third step, our DG sizing calculation. DG sizing calculation, before starting we require that DG data. Let's see here our start time overload coefficient of DG 1.5, DG power factor is 0.8, DG reactance is 0.15. These three data we can get from our client or DG manufacturers. Let's see, now we know that base load of our plant and large size motor starting and running load. Then we know that DG data. Based on these three data, now we want to start our real DG sizing calculation. First method of DG sizing calculation, PG1 normal running condition including 20% of future capacity. That means already we know that our base load KVA 570.33 kVA. From that base load we multiply with our future capacity 20%. This 20% is very depend on your client requirement. If multiply our 120% matlab means 570.33 multiply with 20 percentage future capacity, we can get 684.396 kVA. This is our first size of DG in our calculation. You just remember this is our first sizing of DG calculation. Then you go to second method. You just see PG2 is a second method. In this method, we want to find our DG sizing based on the short time overcurrent. That means you can see here in that DG data short time overload coefficient Kg equal to 1.5. That means our selected DG can withstand 1.5 times of rated load during the starting. So that's here we want to find, let's see here, effective base load kilowatt. This is our formula. Pg2 equal to square root of effective base load kilowatt plus motor starting kilowatt square plus bracket effective base load kVAr plus motor starting kVA or square divided by short time overload coefficient of generator. Short time overload coefficient already we know that is 1.5. So now we want to find effective base load equal to base load kilowatt minus large motor running load kilowatt. That means it's also same like square root of kVA square root of kilowatt square plus kVA square. Here we need to know the DG starting kilowatt. That means we required base load kilowatt plus starting large size motor kilowatt. So during that starting we want to minus our running kilowatt of the DG. So let's see here, effective base load kilowatt equal to base load kilowatt minus large motor running load kilowatt. Already we know that our base load is 449.48. Our large size motor running load 57.38. This 57.38 you just see here, our large size motor running 57.38 is our large size motor running load. Finally we can get 392.10 kilowatt. As it is same kVAr also we need to find. Our base load kVAr is 280.51. During that large size motor running kVAr 35.5. 5 6. So now finally we can get 244.95 kVA, or you just substitute in this value in our formula. We know that already effective base load is 392.10, and motor starting kVA, kilowatt, motor starting kilowatt, you can see here, motor, this is our large size motor starting kilowatt, 110.98. Substitute here and you can get 623.64. And also you know that our DG efficiency is 93 percentage. That means our DG is capable to deliver the load in that in this in that rated power 93 percentage only. So that means we need to, our total kilowatt is kilo kVA, our total kVA is 623.64 kVA. So further we need to divide the our efficiency, we can get final kVA of DG sizing. This is the our 670.58 kVA is our second sizing of DG. So already we know that first sizing of DG is 684.396, and second method we can find 670.58 kVA. The second method already we know that we are selected the DG based on the withstanding capacity of our DG. You see in that our Indian standard IS IEC 60034, AC generators having rated output not exceeding 1200 MVA shall be capable of withstanding a current equal to 1.5 times the rated current for not less than 30 seconds. Also you can, AC generators having rated output above 1200 MVA shall be capable of withstanding a current equal to 1 times the rated current for a period which shall be agreed, but this period shall be not less than the 15 second. Less than 1200 MVA DG as to capable to withstand 1.5 rated times of 30-second load. Here above the 1200 MVA has to be withstand 1.5 times of its rated current with 15 seconds during the starting. And third method, this is our third method, DG terminal voltage drop with a permissive value under transient condition. For example, DG terminal voltage drop is 10 percentage and total voltage drop is 20 percentage from DG to our large motor. if 10 percentage occurred in the DG terminal, hence remaining 10 percentage voltage drop allowed in the incoming and motor side. Let's see here voltage drop at DG terminal. Pg3 equal to RMS kVA plus base load kVA multiply with 1 divided by voltage drop minus 1 multiply with our DG reactance. You can get the DG reactance from DG datas. 1.15 is our DG reactance. Already we know that our RMS kVA. Where we get RMS kVA, we can get our large size motor starting load. This 554.93 RMS kVA we can get from here. This is our large size motor RMS 554.93 kVA. Base load already we know that, and 1 divided by our assumed voltage drop at DG terminal is 10 percentage. So we now put here zero point 0.1 and minus 1 into our reactance is 0.15. So finally we can get 1519.10 kVA is our third size of DG. Finally, this is our conclusion. Based on the 20 percentage, we can get 684.39 kVA, and based on that short time overload withstand capacity, we can get 670.58 kVA, and this is our voltage drop. Based on voltage drop, we can get 1519.10 kVA. Now you can select which one is largest value. That is our requirement of size. You just see here our large size is 1519.10 kVA, and future load purpose we can multiply 15 percentage with this large size, we can get 1746.96 kVA. So for standard size 2000 kVA will prefer for our load requirement, base load requirement. Now you can ask one question. Our base load is only 570 kVA. Then why we required 3 times of more than that DG size? This DG size we are calculating from our voltage drop at the terminal of DG and the value reactance value is our DG is 0.15. Based on this reactance value, we are getting this much of over rating. If it is our DG reactance is more, then this DG size will get reduced. During the DG selection, we have to keep in our mind the reactance of DG. If it is your reactance of DG is more, then your DG sizing, the rated requirement DG size will get reduced. Up to this, we find our requirement of DG. Some let's see some voltage. Let's see some cross verification of our selected DG. That means already we assume some voltage drop here up to DG terminal 10 percentage, then DG terminal to panel, then panel to large size motor, how much voltage drop. The total we are assumed as 20 percentage from DG to motor terminal. 20 percentage of voltage drop we calculate. Let's see here voltage drop calculation at alternator or terminal. You just see here, you just see this is our formula. Percentage voltage drop equal to total starting kVA in multiply with DG subtransient reactance. DG subtransient reactance also we know that 0.15, and DG rating in kVA. This DG rating in kVA, finally we selected 2000 kVA. So this is the which we select DG for our load. Let's see here our base kVA we know that 570.33, and starting kVA we know that 554.93. This is the large size motor starting kVA minus large size motor kVA. The large size motor kVA is 67.87. This is our running kVA. So finally we can get total starting kVA. Our total starting kVA is 1057.39 multiply with our reactance value divided by our selected DG kVA. Total terminal voltage drop is 7.9 percentage. So we assumed 10 percentage. So here we get 7.9 percentage. That is almost less than the 10 percentage of terminal voltage. Second, we can get voltage drop from DG terminal to incoming side. This is the one method voltage drop calculation at the DG terminal. And another method we can find voltage drop from DG terminal to incomer panel. So you just we are selected 6 run multiply single core with 630 square mm. The cable resistance and reactance value we can get from vendor data. The length of total cable is 124 meter. Finally, we can get the current value. The total current is 1565.46 ampere. Our starting power factor is zero point 0.2. Finally, voltage drop calculation VD1 equal to square root of 3 multiply starting current multiply length of the cable bracket resistance of the cable cos pi plus reactance of the cable sin pi divided by number of runs. Here I put number of runs 4, but there selected number of run 6. You can put here number of run 6. This value will get more reduced, less than almost it will go to 5 volt almost. Our aim is only the 10 percentage during the during this DG starting at DG terminal. That means DG terminal to our panel. The voltage drop is only the 10 percentage. So it is a more than it is almost less than that 10 percentage. And second, voltage drop from motor feeder switch gear to motor side. Our cable you just selected cable is 3 into 3 core 120 square mm. The total length is 140. As it is, you can see that voltage drop formula here, and you can get total voltage drop here 16.70 VD1 plus VD2. That means generator to VD1 generator to switchgear panel, then VD2 switchgear panel to our motor. So total voltage is 24.55 volt. The motor is running with 415 volt. This total voltage drop is 5.9 percentage. Already we decide 20 percentage is allowed for motor starting terminal. That means more from DG terminal to motor 20 percentage is allowed. Now we get only that 5.9 percentage of voltage drop. You just see here. Next one is our reference. Cable size for large motor is verified as follow. See, for large size motor, we selected 120 square mm, 120 square mm, 3 core, 3 run. So that cable size is enough to feed the power to our large size motor. That we need to verify. So same as it is, resistance of cable and reactance of cable from that get our vendor data. The total length is 140 meter. Then our large size motor kilowatt is 75. Rated efficiency of our large size motor is 0.954. Rated power factor, we know that 0.85 from the tabular column we can get. And you just you make a calculation. You just put here, we need to find ampere of the large size motor. Here 128.67 is our large size motor ampere. Then we put here vd 0 equal to square root of 3 multiply starting current int length int resistance cos phi plus reactance sin phi divided by number of runs. Finally, we can get 9.14 volt. Almost it is a 2.24 2.2 percentage of 415 volt. Therefore, 3 run 3 core 120 square mm is enough for feeding the power to our large size motor. You just see another verification at fault level of 100 kA and short circuit clearance time of 0.25 second. The minimum cross section of cable will be S equal to 100 multiply with 1000. This is a kilo ampere. 1 lakh kilo ampere multiply root of 0.25 divided by this our cable, aluminum cable constant 144. Finally, we get 347.22 square mm. That means we selected 3 run 120 square mm. Almost that means we 120 square mm 3 run means 360 square mm we selected for large size motor cable. And finally, they required the short circuit rating of our required size is 347.22. So it is almost lesser than the our selected cable. Hence, the conclusion is our selection is correct. Thank you for watching our videos. If any comments, please write in below. Thank you. Thank you.